Welcome back to Physical Science 101. This is our second lesson of Unit 6, Light, and it's going to be our first of two lessons on the interaction of light with matter. So let's get started. Matter can either emit, reflect, transmit, or absorb light, and all of these can be wavelength or color dependent and polarization dependent. So let's take a look at this diagram to see what we're talking about with each of these processes. In this diagram, you'll see a ray of light or a beam of light marked as incident light. So that is the light that is shining on this cube of matter. Now, when the incident light hits the surface of the cube of matter, it can bounce off. That would be reflection. So the incident light bounces off of the surface and gives us reflected light. We can also have the light penetrate the surface and be transmitted through the object. So the ray of light that goes through the object is transmitted, and some of the light can be absorbed by the matter. So this block of matter can reflect light, absorb light, or transmit light, or do all three at the same time. But first, that light had to come from somewhere. That incident light had to start from somewhere, and that would be light emission. So the first thing we're going to talk about is the emission of light by matter. So we break down the emission of light by matter into two processes, one of which we call incandescence and one of which we call luminescence. Incandescence refers to thermal radiation, or in other words, light that's given off by a hot object. All objects that have a temperature above absolute zero give off light, and that would be incandescent light. Now, some of the properties of incandescent light are that it has a broad spectrum, meaning that it gives off light at many different wavelengths at the same time. Another property of incandescent light is that the intensity of the light emitted increases with temperature. So the higher the temperature of the object emitting the thermal radiation, the more intense the light coming from that object. And another property of thermal radiation is that the peak frequency, or the frequency at which we have the most radiation, that also increases with temperature. So as the temperature increases, the frequency of the light increases, or in other words, the wavelength of the most intense light decreases with temperature. Let me demonstrate that for you. Okay, what we have here is a graph of wavelength from low wavelength to longer wavelength, and you can see the visible spectrum in here. We have the violet, blue, green, yellow, some orange, and some red. So red has the longest wavelength, violet has the shortest wavelength. And so on this side, to the right of red would be infrared, and to the left, or to the shorter wavelength side of violet, would be ultraviolet. So this is the spectrum from ultraviolet to visible to infrared. And this curve here shows you the spectrum of a black body, of thermal radiation with the temperature same as the sun, 5,800 Kelvin. So this is a very hot object. It is hot enough that it is glowing very strongly in visible light. So this curve says that you have some purple, some blue, most green. So the sun spectrum peaks in the green. The color of light that is brightest in the sun is the green, and then less yellow, less red. So there's more green than anything else, but all of this light together, all of these colors together give us white light when we blend them together, just like an white incandescent light bulb. Now, you can see that the sun does give off more visible light than anything else, but it also gives off a significant amount of ultraviolet light. So there is part of the spectrum that is in ultraviolet. That is why you tan when you're in the sun. And it also gives off infrared light, gives off a lot of infrared light. That is why you get warm when you stand in the sun. There's a heat flux of infrared radiation from the sun to you. And so the sun is giving us infrared, visible, and ultraviolet. So that is a 5,800 Kelvin object. If I were to lower the temperature, so I'm going to come over here and I'm going to lower the temperature. As I lower the temperature, notice that two things are happening. One is that curve is decreasing at all wavelengths. So I've lowered the temperature to 4,750 Kelvin, and notice that we're giving off noticeably less radiation at all wavelengths, less ultraviolet, less visible, and less infrared. So the lower the temperature, the less radiation, less thermal radiation we get from the source. And also notice that this peak right here is in the yellow now. So the peak has moved to longer wavelengths. It's moved from green to yellow. So this less hot object is giving off yellow light. I'm going to lower the temperature some more, and notice that the peak has now gone into the red. And note, so two things. One is the peak has moved to longer wavelengths, or it's moved to red, and the radiation at all wavelengths has gone down. Now this is getting pretty low, so I'm going to zoom in. I'm going to click this plus right here, and you'll see that the top of the scale right here is 100. The top of the y-axis is 100. I'm going to zoom in, and it goes to 20, so that lifts up our curve. So we've zoomed in on the curve and raised that up. Okay, so I'm going to keep lowering the temperature until we get to the temperature of a light bulb. Okay. And I'm going to zoom in again. We're going to go from 20 to 4. Okay, so this is the spectrum of an incandescent light bulb, a light bulb that gives off light by being hot. A couple things to notice here. One is it does in fact give off visible light, so we have visible light here, but notice that more than anything else, it gives off infrared. So that is why incandescent light bulbs are considered to be inefficient. Most of the radiation that they give off is in the infrared. So most of the radiation from a light bulb is in the infrared. Only some of it is in the visible. So it does give off visible light, but it gives off a lot more infrared or heat. And it's about maybe a fourth visible and about 3/4 infrared. So incandescent light bulbs are more effective as heat sources than they are as light sources. Okay, I'm gonna keep lowering this. I'm gonna lower it down, 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 down. We're still at a pretty high temperature, 1,950 Kelvin. So I'm gonna zoom in on the y-axis again. Oops. Actually, I'm going to keep zooming, going down. So I'll keep lowering the temperature. Okay, zoom in, raise that back up. Keep lowering the temperature. Okay, zoom in. And now notice that my spectrum has gone really off to the infrared. So I'm actually going to change I'm going to zoom out in wavelength. So this is 3 micrometers in wavelength. Now it's 6. And let's see, I think I've zoomed in too much on my, there we go, zoomed in a little bit too much on my y-axis. So I'm going to keep zooming out on the x-axis. There we go. Okay, so that we're going to go down in temperature some more. We're getting closer to the temperature I want. Zoom in, zoom in, zoom in, zoom in. And just a little bit lower, get down to about 300 Kelvin. Okay, 300 Kelvin. Oops, wrong way. Okay, so 300 Kelvin is the temperature of a person. So this is the spectrum of light that a person gives off. You'll notice that visible light is way over here, so all of this is in the infrared. So a person does glow. A person glows in infrared. A person gives off thermal radiation in infrared. And notice that this number has gotten pretty tiny. So we don't glow nearly as brightly as the sun or nearly as brightly as a light bulb. We still do glow very faintly in infrared. So that's incandescence. The other type of light emission is luminescence or non-thermal radiation. One type of luminescence would be fluorescence, which is the process by which fluorescent light bulbs give off their light. One property of fluorescence is that it gives off light in spectral lines. So instead of a broad spectrum of light emission, you get very precise frequencies of light being given off, or very precise colors of light being given off. Let me demonstrate to you the difference between an incandescent light bulb and a fluorescent light bulb. Okay, what I have here is an incandescent light bulb. That means that this is a light bulb that gives off light because it is hot. It is hot enough to glow in visible light. This is an old-fashioned light bulb. And what I also have are spectral glasses. And what spectral glasses do is that they break up light into its spectrum. Now I'm going to give a pair of glasses to the camera so that you can see what I'm seeing. Okay, what you see here is you see the light bulb right here giving off white light, and over here you see the spectrum of that light. So you see that this white light contains red, orange, yellow, green, blue, and some purple right on the end. Okay, so this white light here actually contains all of these colors, contains all the different colors, and that's because this is thermal radiation, and thermal radiation contains a continuous spectrum of light. Now that is different than a fluorescent light bulb. I'm going to take this light bulb out and I'm going to put in a fluorescent light bulb, or a newer type of light bulb. That is really hot. I can tell you it is giving off light because it is hot. And here's our fluorescent light bulb. And what you will see now is that it also gives off white light. So we have white light over here, but now you can see distinct colors in here. You don't see a continuous spectrum. You see a red light bulb, a yellow light bulb, a green light bulb, a blue light bulb. So you see distinct colors. So this light bulb glows by fluorescence. It gives off light only in particular colors. So each color of light that it gives off, you see as a distinct different color light bulb over here. Okay, so that is the difference between an incandescent light bulb that gives off thermal radiation and has a continuous spectrum from red to purple. You didn't see distinct light bulbs. You didn't see distinct incandescent light bulbs over here the way that you see these distinct fluorescent light bulbs in their different colors. You just saw a blur of color continuously from red to purple. And another thing about the incandescent light bulb is it also gives off a lot of infrared radiation because it's so hot. So that is why the fluorescent light bulb is more efficient than the incandescent light bulb. With the incandescent light bulb, maybe only about a fourth of its energy actually goes to light, goes to the light that you can see here. The rest goes into infrared radiation, which is off to the side, which we can't see. Okay, so one more thing while I have the spectral glasses on the camera is you see that this light bulb is giving off white light, and you see that white light is made up of a continuous spectrum, a smooth spectrum from red to purple. I also have some filters. I have a red filter here, and what I'm going to do is I'm going to turn this white light red by putting the filter in front of it. So now you should see it as a red light. And how did I turn that light red? Well, what I did was the filter absorbed all of the light other than the red. So you see there's your purple, green, blue, yellow, and the filter absorbs all of those and only lets the red light continue. So the filter turns the white light into red by taking out everything except the red. Okay, and I can do the same thing. I have a green filter here. I'm going to turn that light green, and the way that I do that is that the filter absorbs everything except the green light. So now the light appears green because we've taken out all of the light over here, and left the green. So we're filtering out all of this light, and we're just leaving the green light. Same thing for blue. I have a blue filter right here. When I pass the blue filter in front, the light appears blue now, and that's because we've taken out everything over here and just left the blue. Okay, a quick question about incandescent light emission. An object is hot enough to emit a dull red glow. When this object is heated even more, it will emit A, more visible light and less infrared, B, less visible light and more infrared, C, more infrared and more visible light, or D, exactly the same amount of infrared and visible light. So please pause and think about that, and when you've definitely come down on an answer, hit play, and I will talk about the correct answer. Okay, as we saw in the simulation, when the temperature of a glowing object is increased, it gives off more light at all wavelengths. So as the object is heated even more, it will give off both more infrared and more visible light. So the correct answer is C, more infrared and much more visible light. That was the emission of light by matter. Now let's talk about the reflection of light by matter. We break down reflection of light by matter into two categories, the first of which we call specular, or mirror-like reflection, and the second we call diffuse reflection, which we also call scattering. Now, specular, or mirror-like reflection, happens on very smooth surfaces. That's like the top diagram. And in specular reflection, the angle at which the light comes in is the same as the angle at which the light reflects. Or in other words, the angle of incidence equals the angle of reflection. And what that means is that all the reflected light goes in the same direction as in the top diagram. Now, diffuse reflection is the middle diagram, where we have the light coming in, but since we have a rough surface, the light bounces off in all directions. So everywhere that the light hits, actually the angle of incidence equals the angle of reflection, but now the angle of the surface changes so that when the light comes in, the light bounces or reflects in all different directions. Let me demonstrate that for you. Okay, what I have here is a sheet of white paper, and the reason that you can see the white paper is because that there are lights here in the studio, and those lights are shining on the paper, and the paper is diffusely reflecting the light, meaning that the light hits the paper and goes off in all directions. Some of it goes towards the camera. So no matter what angle I hold the paper at, you will always see some light reflecting towards you. Okay, so no matter which way I turn it, you're going to see light from the paper because the light hits the paper and goes off in all directions, some of which is captured by the camera for you to see. Now this tiny black spot here is actually a mirror. And the reason why it looks black is because the light that hits the mirror, the light from the lamps in here that hit the mirror, don't undergo diffuse reflection. They undergo specular reflection, meaning that all the light bounces off in a particular direction. And since the lights are above me, they hit the mirror and bounce down, and none of that light goes to the camera. So that's why the paper looks black. I mean, why the mirror looks black. So the paper looks white because light is bouncing off to the camera for you to see. The light that hits the mirror actually bounces down all in one direction where you can't see it. So if I want you to see the light in the mirror, if I want to make the mirror bright, then I will have to hold the paper at a particular angle so that light from the mirror gets to the camera. And there you see these bright flashes of light. That is when I have the lights, when I have the mirror angled just right so that the light from the lamps bounces off of the mirror right to the camera. So the mirror goes from being black to being brilliantly white whenever we have the right angle so that the light goes to you. So that is the difference between diffuse reflection and specular reflection on the mirror. So diffuse reflection or scattering is how we see objects that do not emit their own light. Like for example, you can see me even though I'm not giving off visible light. I am giving off infrared light, but this video is not in infrared light. This video is in visible light, so you can see me even though I am not giving off my own visible light. How can you see me? Well, off to the side of me are lights that are shining light onto me, and when that light shines onto me, that light scatters off into all different directions, some of which goes to the camera. So light comes to me, scatters in all different directions, and some of it goes to the camera. So I don't have to arrange myself in a particular angle for light to go from me to the camera. The light comes and scatters off in all directions, so wherever we put the camera will pick up some of that light and be able to see me. This is similar to the bottom diagram with the student looking at the tree. Sunlight hits the tree, and that light, when it hits the tree, scatters off in all directions, some of which goes to the student in the desk. So that is how we see objects that don't give off their own light. They diffusely scatter light, and we can see it in all different directions. Now, reflection and absorption can depend on wavelength, and if they do, then we perceive that as the color of the object. So, for example, I'm wearing a blue shirt, and the reason it appears blue to you is that even though white light is shining on me, and it is white light is shining onto me, and then my shirt absorbs all of the light except for the blue light. The blue light is what it reflects or scatters. So the light shines on me, the white light shines on me, the red gets absorbed by my shirt, the orange, yellow, green, all of that gets absorbed to my shirt. What my shirt reflects is the blue light. So you see my shirt as blue even though white light is shining on me. Now even air scatters light. That's how we see a blue sky. So when the sunlight shines through the air scatters light, and it preferentially scatters blue light, and it preferentially scatters light of shorter wavelengths. So as the sunlight goes through the air, the blue light gets scattered out into all directions. So no matter which way you look, as long as you're not looking directly at the sun, no matter which way you look, you're going to see blue light scattered from the sky towards you. That's why we have a blue sky. Now, when the sun gets very low in the sky and all of the blue light has been scattered out, then like at sunset, sunrise or sunset, we can look at the sun and we see the light that is not scattered, which is the red light. So that's why the sun appears red when it's setting, because when the sun is setting, the light has gone through a lot of air. All the blue light has been scattered out in all different directions, and the only thing that's still coming towards us is the red light. So reflection can affect the color of light. It can also affect the polarization of light, which explains why we wear polarized sunglasses. Here we see light from the sun reflecting off of a puddle on the surface of the road into the eye of a bicyclist. Now, the light from the sun is unpolarized, but the light from the puddle is horizontally polarized, and that is because the surface of the puddle is also horizontal. So a horizontal puddle will reflect light that is horizontally polarized. And what this means is that the bicyclist can actually block the light from the puddle by wearing polarized sunglasses that are vertically polarized. So vertically polarized sunglasses will block the horizontally polarized light from the surface. So it will block the glare from the sun. Let me do a demonstration to show you that. Okay, what I have here is a polarizing filter. Now what a polarizing filter does is it only lets through light with a particular polarization. Now the way we know the polarization that it lets through is that it has two little marks here that I'm going to keep my fingers on so that you can see which way the polarizer is oriented. So right now my fingers are horizontal, so that means that this filter will let through horizontally polarized light. So it only let through light that is horizontally polarized. If I rotate my fingers like this, then the polarization is vertical, so this filter will now let through vertically polarized light. Now the camera also has a polarizer on it, and the purpose of the polarizer is to reduce glare, just like your polarizing sunglasses. And the polarizer on the camera is oriented vertically. So the polarizer on the camera is oriented vertically. So I'm going to put the polarizer in front of this incandescent light bulb. The incandescent light bulb gives off both vertically polarized light and horizontally polarized light. So what you're seeing right now through the polarizer of the camera is just the vertically polarized light. So I'm going to take this filter and notice that I have my fingers vertically oriented so that the filter will only let through vertically polarized light. Now if I put the filter in front of the light bulb, then you should see really nothing change, because the filter was already letting through vertically polarized light. My filter is letting through vertically polarized light. So any light that goes through my filter will also go through the camera's filter. Now that will change if I rotate the filter to only let through horizontally polarized light. Okay, so now I'm only letting through horizontally polarized light through my filter. So the horizontally polarized light goes through my filter, but now the filter in the camera blocks it. So you can still see around my filter because that has vertically polarized light in it, but the light that goes through my filter is only horizontally polarized and will not get to the camera. So that's why the part of the light bulb that's behind my filter looks black. I can rotate it again so that to give the camera vertically polarized light that it can see. I can rotate it back to only let through horizontally polarized light that the camera can't see. Vertically polarized light, horizontally polarized light. So with the vertical filter on the camera, the camera cannot see horizontally polarized light, which is what's getting through my filter right now. So it looks completely black to you. One more time. Vertical, horizontal. Okay, if you take a look at this spot of light here, this is the reflection of a light that's up on the ceiling. Imagine that you're driving down the road and that is a street light or the sun reflecting off of a wet road. That would be pretty blinding to you, pretty glaring. But we can actually get rid of that with a polarizer. The camera that you're looking at actually has a polarizer on it, and the polarizer is oriented horizontally right now. And that's how you can actually see this spot, because when the light comes down, it reflects off, and the light that's reflected is horizontally polarized. So all of the light that reflects off of the floor is horizontally polarized, and since the polarizer on the camera is also horizontal right now, the light gets through to the camera. But if we were to turn the polarizer vertically, like your vertically polarized sunglasses, then that light will not be able to get through the polarizer, and you will actually not be able to see it, and you'll be able to see the road instead of the glare. Okay, for our final demo of this type, we've moved the camera outside of the University Center, and I'm on the inside, but you can't see me because of the reflections off of these windows. The reflections on the windows are vertically polarized now because the windows themselves are vertical, and since the polarizer on the camera is vertical, all of the light from these reflections is getting into the camera. But we can fix that, however, by turning the polarizer horizontally, and then the light from the reflections will not be able to get into the camera, and you should be able to see me. Okay, let's wrap up this lesson with some questions. The first is, green grass reflects A, yellow light, B, green light, C, blue light, or D, white light? Think about it, pause, think about it, and then when you definitely have an answer, hit play again. The correct answer is B, green light. Green grass appears green because it reflects green light to our eyes. So even if white light shines on green grass, the light that is reflected is the green light, which is why it appears green to us. So the correct answer is B, green light. Next question. Green grass absorbs A, yellow light, B, only green light, C, blue light, or D, all light but green light. So think about this, pause, think about this, and when you have what you think is the best answer, hit play again. And the best answer here is D, all light but green light. So if white light were to shine on green grass, that green grass would reflect the green light and absorb everything else. So that's another way of saying why green grass is green, because it absorbs all of the light but the green light and then reflects the green light to us. So the correct answer is D, green grass absorbs D, all but green light. Next question. You are able to see objects that do not emit their own light because light from another source undergoes A, absorption, B, diffuse reflection, C, a change in speed, or D, refraction when it hits them. So please pause, think about it, and hit play when you're ready. The correct answer is B, diffuse reflection. You are able to see objects that do not emit their own light because light from another source undergoes diffuse reflection when it hits them. Or in other words, the light from the source hits the object and that light goes out in all directions, and you can see that object no matter what angle you look at it from. So the correct answer is B, diffuse reflection. Next question. We see a blue sky because A, air molecules absorb more blue light than red, B, air molecules reflect more red light than blue, C, air molecules scatter more blue light than red, or D, the sky is very hot. So please pause, think about it, and hit play when you're ready to hear me talk about the correct answer. The correct answer is we see a blue sky because C, air molecules scatter more blue light than red. The blue light that we see from the sky is sunlight that has been scattered to our eyes. So the correct answer is C, air molecules scatter more blue light than red. Last question. Polarized sunglasses work best in eliminating glare because A, reflected light is refracted upwards, B, unpolarized light vibrates in all possible directions, C, reflected light undergoes dispersion, or D, reflected light is polarized in a horizontal direction only. So pause, think about it, and when you're ready for the correct answer, hit play again. And the correct answer is polarized sunglasses work best in eliminating glare because D, reflected light is polarized in a horizontal direction only. So your polarized sunglasses are vertically polarized, meaning that they block horizontally polarized light. So the polarized sunglasses eliminate glare because D, the reflected light, is polarized in a horizontal direction. That is the end of this lesson. In the next lesson, we're going to talk about the transmission of light through matter. Until then, think science.